Hi, I'm John Ceccarelli, Senior Director of Product Management here at Azul Systems, and today we're here to talk about Ready Now and Ready Now Orchestrator. So today we're going to talk about one specific set of benefits that Azul Platform Prime brings, and that is faster Java warmup. So in this webinar, we're going to look at what Java warmup is, how it can affect your business, and how Azul Platform Prime solves the Java warmup problem with Ready Now and with Ready Now Orchestrator. So let's get started. So Java is a write once, run anywhere language. That means that the source code that I write and compile can run on any system that Java supports. So as a developer, I write a bunch of source code, and then I run it through the Java-C compiler, and what I get is an artifact like a jar file or a war file. And then I can use that file and I can deploy it to any system that the JVM supports, whether that's Mac, Windows, Linux, x86 machines, ARM64 machines. I don't have to compile a different version of my program for every different type of machine on which I want to run my application. So in order to run on all types of servers and still be fast, Java performs a second type of compilation at runtime called just-in-time compilation, or JIT compilation. And we're going to take a quick look at this, just a very high-level overview. So when you first start running, you run in what's called interpreted mode. So this is running that portable bytecode that got produced in the last step. This can run anywhere, but it runs very slow. So as you can see, with speed on the y-axis and time on the left axis, the yellow bit has the lowest speed of all of our types of code. And during this time, we're basically just trying to figure out which parts of the code is hot, which parts of the code are being called a lot of times. So when you reach a threshold, it's usually 10,000 times that a certain piece of code has been called, the JVM will say to the compiler, hey, take this method and try and make it better for me, right? Try and compile this and make this run faster, right? And that's when you get into the C1 tier. So we compile it a little bit and it runs a little bit faster, but still nowhere near the maximum code that we're going to get. And at this point, what happens is the compiler and the JVM have this kind of conversation where the compiler asks a bunch of questions of the JVM about how is this code being used? What types of things are happening in this code? Get all of the information that it needs in order to produce the final level of code, which is the C2 compiled code, right? And this is the code that will eventually run at your top speed, right? And once all of the methods that are being called regularly are have been compiled, that is when we reach our steady optimized state. And it's important to note that this isn't a straight line. There are times along this line where you'll see additional dips. That's where the compiler made some guesses based on the information it had up till that point, right? About what the best way to optimize a piece of code was. And then what happened was that the usage changed. It turned out that people started using the code in different ways, right? And the guesses that the compiler had made turned out to no longer be true. When that happens, we get what is called a de-optimization. That's when a certain piece of compiled code turns out to no longer be valid, and we have to throw that compilation out and go all the way back to interpreter mode, then asking the questions in order to form a new compiled method, and then compiling that. And as you can see by the dips in the blue line, what happens there is that when that happens, your code actually slows down. When you have a de-optimization, and especially when you have what's called a de-optimization storm, where you have a whole bunch of methods that have to be thrown out, you will get dips in your actual code speed. So it's a lot of information to take in. The main things to understand here are that Java needs to have this conversation between the JIT compiler and the JVM every time it starts up to build what's called a profile. a profile of what the hot methods in the code are that need to be compiled and how what the information we need to correctly compile those things. And the second thing that you really need to notice here is it takes time, right? From when you first start your Java program to when it reaches that steady optimized speed takes a bit of time. So one of the most common problems of slow Java warmup is that you'll get bad performance at the most critical time. So if you have a system set up, like let's say a shopping cart system, and you have this set to scale horizontally, meaning as load increases on the system, you'll spin up new instances to handle that load. Let's say you have a shopping cart, and normally it takes you 5 instances of your shopping cart to handle your usual amount of traffic. But all of a sudden, you get a spike in shoppers, which makes you happy. Yay! So what do? You scale out 5 more instances of your cart in order to handle that spike of shoppers. Problem is that because that code is not warmed up, those customers are going to have a bad experience if they get directed to those new shopping cart instances, right? And so with that bad experience, you're going to have a high cart abandonment. You're going to lose a lot of that business that you could have gotten, which in turn will make you unhappy, right? So how do people deal with this? Well, what they do is they try and artificially warm up a JVM with fake transactions before they let them accept traffic. So let's say you start up your JVM and you say, before I handle any real shopping on this thing, I need to run a bunch of fake shopping orders through my shopping cart in order to get the compiler to optimize all the code that I need in order to handle real ones. So I run a bunch of fake transactions and I wait for 15 minutes and then my JVM is warmed up and now I can start actually shipping some of those shoppers to my new shopping cart instance. Well, I mean, one of the problems here is, of course, it took you 15 minutes, right? It took you 15 minutes. By that time, you may have lost a lot of your shoppers. It also adds other complexity, right? So how do you tell the fake transactions from the real transactions, right? You wouldn't want to all of a sudden have your warehouse start shipping orders to a bunch of fictional consumers, right? And this is something that can obviously be handled, but it adds complexity, right? Another thing is that it's very hard to write a script that's going to mimic the real customer usage. So you run the risk that certain parts of your code won't be touched the right way, or that the compiler will make some of these incorrect guesses that we talked about that lead to deopt storms, right? And of course, the most important thing is, you took 15 minutes. That was 15 minutes of customers who were having bad experiences because they were on the old overloaded JVMs, right? This also limits the way you deploy changes to code. CI/CD, continuous integration, and continuous development is a very modern practice where we deploy changes all the time to your live set of applications. As in, any new change is ready, you deploy it immediately. And what this means is very, very frequent, multiple times a day frequent restarting of your entire fleets of JVMs. And if you have a serious Java warm-up problem when you restart all those JVMs, you're going to be less aggressive in how quickly you deploy new changes to your applications. In the end, the way a lot of people deal with that additional complexity and with that long time before new instances can actually handle traffic at speed is to just over provision, right? So you're either not taking full advantage of cloud elasticity, right? We have this wonderful magical cloud that can bring up new resources at any time fairly quickly, but we don't take advantage of it because we're afraid of how long it takes our Java code to reach full speed. And that means what we do is we keep a lot of resources sitting around, running, not being utilized, just in case we need them. So I have the shopping carts that I really need, and then I have the shopping carts that I keep around just in case. This all leads to wasted money and higher cloud costs. And finally, there's even a cost that occurs after you're fully warmed up, and this has to do with those de-optimization storms that we talked about. That's because the default JIT compiler only compiles for the usage that it's seeing right now. And if that usage changes, it needs to recompile a bunch of stuff, and that leads to slow code. So here's a very, very simplistic example. Let's say that you have a trading application, and in the morning, everybody is just buying. So the JIT compiler will look at that and go, I guess everybody just buys on this application, and it'll optimize its code for patterns that only exercise buying. And then you get to later in the day, and all of a sudden everybody starts selling, right? So what does the JVM do? It says, oh, better throw out all this compilation work I did for people who were just buying and recompile for somebody who both buys and sells. And what happens there is bad performance. On a stock trading system, that would mean lost orders, that would mean real money. So years ago, Azul looked at this problem, and we asked ourselves the simple question, why are we profiling on every run? Of course, yes, you need to profile on the first run when the JVM has never seen this code before, but you never run a piece of code just once, right? You restart your JVM all the time, right? And you have entire fleets of JVMs that are running this same code. So the question is, why can't a JVM remember what it did last time? Why can't a JVM ask its buddies in the fleet of code that are running the exact same code what it should do? In other words, why aren't we saving that profile information that we generate and reusing it on subsequent runs so we don't have to go through that whole profiling curve again, right? So that's exactly what Azul's Ready Now does. Ready Now is a part of Azul Platform Prime, which is our hyper-optimized build of OpenJDK, right? And what Ready Now does is it saves your profiling information so that it can be reused on the next application. So instead of going through that whole process of interpreted mode and C1 profiling and asking all the questions so that I can then optimize my code, I can just jump right in and just start optimizing that code immediately, right? So the end result is that it gets your code to steady optimized state as fast as possible. The other thing that Ready Now does is it doesn't just look at what's my code doing right now, but it looks at what's my code likely to do over the entire run of my application. So if you think back to our trading application that in the morning did buy, and in the evening did sell. Well, a Ready Now profile will know that during the course of the day, I'm going to have both buys and sells. So it's going to produce optimizations that will be able to survive both those usage patterns. And in that way, it's going to avoid that de-optimization storm. It's going to make sure you have consistent performance throughout the entire life of your JVM. And at the end of the day, this just means you've got reduced CPU resource consumption. It just means you can handle more business processes, more workloads with less CPUs, right? And it means that you're going to be more likely to use containerization. You're going to be more likely to take advantage of cloud elasticity. And in the end, you're going to spend less money handling your Java workloads. That's a lot of words, but really what we're talking about is turning this into this, jumping straight into highly compiled code that stays fast throughout the entire run of your JVM. So Ready Now isn't something new. It's something that's been in Azul Platform Prime for years. And over those years, we've learned some things about how people want to deploy with Ready Now. So the first thing we learned is that generating a profile today with Classic Ready Now was an additional step in the deployment process. It meant you had to change your deployment process to manually generate a profile that could then be used for other JVMs. And once you had that profile, you had to figure out how to actually get it to the JVMs, right? And this is especially difficult to do when you're using containerized environments, right? So if you're building applications in containers, You either have to bake the image straight into the container when you build it, or you have to set up some persistent storage in order to make it accessible. Just in many ways, it's very difficult to get this kind of resource, get this profiling information to the JVM so they can actually use it. And additionally, this process was based on just measuring one single JVM, right? Instead of, if I've got a whole fleet of JVMs, measuring a larger set of JVMs and picking the best profile, rather than just measuring one JVM that I'm manually saying record this specific usage pattern. So at the end of the day, what did that lead to? That led to an inability to propagate these profiles to containers in a way that was really operationally viable. And lots of people who would have otherwise used Ready Now, especially in containers, were not able to use it. So we looked at this and we said, what if we do this more intelligently? And what if we put the cloud to use to do this? And that's where Azul Optimizer Hub comes in. Azul Optimizer Hub is an existing feature of Azul Platform Prime. And Azul Optimizer Hub is a set of services that lets JVMs collaborate to run more efficiently. There's two main features of Optimizer Hub. So one is the cloud native compiler. And what that does is basically allow you to actually ask a separate service to do all your JIT compilation for you, so you don't have to do it on the machine. And the second thing was this new feature that we're introducing today, which is Ready Now Orchestrator, right? Ready Now Orchestrator streamlines the process of using Ready Now in fleets of containerized JVMs. And we're going to talk about exactly how it does that in a second. So, but before we do, let's speak a little bit more about what Optimizer Hub is. Optimizer Hub is a Kubernetes cluster that you configure and you run in your cloud or on-prem, can work in both, right? And so it's inside of your firewall. It's not a managed SaaS that you have to set up open ports in order to communicate with. So it all runs inside of your estate. Optimizer Hub is also free for all Platform Prime customers. There's no additional contracts to sign. There's no additional bills to pay. Any licensed JVM that uses Platform Prime can also use Optimizer Hub. So what does Ready Now Orchestrator do? Basically, all you do instead of manually recording a profile is you pass a few parameters to the JVM. And based on those parameters and the defaults that are configured on Ready Now Orchestrator, Ready Now Orchestrator will automatically capture profiles, and it'll capture profiles from a subset of all the JVMs that you're running. It'll even take care of doing multiple training runs. So if you want to run a profile through 2 or 3 times to make sure that you've got the best possible optimizations, it will do that for you automatically, right? And then whenever a JVM requests a profile, it'll automatically look at all of its candidates, pick the best one, and stream that directly to the JVM without having to configure any persistent storage or bake any files into the container images. So right there, right out of the box, the JVM, just by passing a few command line parameters, gets the profiling information that it needs in order to get that really, really lightning fast warm up that we talked about. So basically a JVM wakes up and it says, hey, I'm running this app. It asks Ready Now Orchestrator, do you have a profile for this app? Ready Now Orchestrator, if it has one, looks at all its profiles and gives it the best one. And then Ready Now uses that information to tell Falcon, which is Azul Platform Prime's JIT compiler, to start compiling things right away. And if you want, optionally, you can also have Falcon ask Cloud Native Compiler to perform those optimizations instead of performing them locally. That means that those optimizations will get done more quickly, and you'll use less resources on your client JVM to get them. At the same time, Ready Now is going to also write back more information back to Ready Now Orchestrator about the usage patterns it's seeing, so that the next time Ready Now Orchestrator is asked for one of these profiles, it can provide the best, most up-to-date profiling information based on all of the usage that we're seeing across the entire fleet of JVMs. So we have some early adopters of this functionality, and they are very excited about it. There's one large global retailer and e-commerce company which has Ready Now Orchestrator live in multiple regions of their cloud. They have 40 different applications using Azul Platform Prime, and they've already transitioned some of their applications to using Ready Now Orchestrator, and the engineering and operations teams are excited to see that they can retire their hand-coded solutions that they had before about manually generating these profiles and getting them into containers. Now, with Ready Now, this customer saw a reduction in warm-up time from 25 minutes to 5 minutes. That means that instead of having to wait 25 minutes before they could start letting their shopping carts accept traffic, they were able to do that in under 5 minutes. And they estimated that that 20 minutes of saved time was saving them hundreds of thousands of dollars per instance on slow orders and cart abandonment. So today we've looked at the Java warm-up problem. We've looked at how it can cost you money and cause problems for your business. And we've looked at how Azul Platform Prime solves this problem with Ready Now and Ready Now Orchestrator. I hope you found this talk interesting, and we look forward to hearing from you soon.